can I do this? Is it tempting to do that? But why can't you? Awesome. That was perfect. It's a function, not grouping, right? Those lines mean what?
Absolute value.
Awesome. That's the name, absolute value. And which means what?
Distance from 0.
Anyway, so good job. The graph for this, by the way, I don't know if I've ever shown you that, but not for this specific equation, but I'm talking about the absolute value graph. Looks like a V. Like that, kind of. And so if it can graph its own shape, it's probably a function and can't distribute. And like Jackson said, it's not grouping. So what do we do instead?
Add 3 plus 2.
Oh, can we do that? Is that okay? To make that a 5?
Yes.
No, sorry. Wrong answer. Why can't you do that? This is actually a pretty big deal because that's a common mistake, but one that shouldn't be made. Because can you add before you multiply? Like if we zoom way in on this, there's a little multiply right there, right? It's 2 of these absolute values. Can you add that before you multiply? No. So what can we do instead? Let's subtract 3. Subtract 3. And good grief, I can't write. And we'll get 12. Okay, so how do we get rid of the 2? We can't distribute it. We couldn't add it to the 3. So what do we do now?
Divide.
Yeah, it says 2 times, so let's divide by 2. And we'll get 6. All right, now we're ready to split, and we're doing both positive and the negative, or the opposite and the regular case, if you remember that language. So we take the opposite of the right side and the normal, or maybe the as written. Positive or negative, we say. And we drop the absolute value. And make this side negative. So negative and then 6. Okay, the other side we drop the absolute value also, but we just leave the 6 positive, something like that. Okay, now we have these 2 dinky little equations to solve. Yep.
When I learned this, I thought it was supposed to be like you invert the equation, like 4x minus 5 goes into minus 4x plus 5 equals 6.
Yeah, you can do that too if you leave the 6 alone.
All right.
So he just said it this way. If I change the signs of the left side, then I have to leave the right side alone. So, but do you see how in this case it's way easier just to change the 6?
Yeah.
Okay. All right, let's solve this. What's the first step, JC? These 2 little equations.
Probably 4 minus 5. I don't know.
You guys did good on this stuff. Did you forget it in the last few weeks? You know how to solve this. Like, what is a good first step? Okay, I guess we need to get back into doing this again. Yeah, you can't add 4x and negative 5 because only one of them has an x. They are not like terms. Okay, so add your 5, and we're working to get x by itself. And then how do we do that now? Divide by 4. We'll get x equals negative 1/4. So that's one option. Okay, JC, how about the other side? All right, we'll add 5. Same as we did. And then 4x equals 11. Now what? Yep. Try to work to get that x by itself. X equals 11 fourths. All right. Are they wrong because they're not whole numbers? You know, like if we did this left one, it's negative 0.25. This one is, the one on the right is positive 2.75. So are they wrong? No. All right, it also said, if you noted, write this in interval notation, and it also tells us to graph. So, I'm not sure why I wrote that on there, to be honest, but that's okay. I know some of you got graph paper, but if we're graphing these solutions, we're not using like a line, we're using a line, number line graph, is what kind of that is looking at. Now, this is not an inequality, so like I said, I probably shouldn't have put that on there. Let's do a quick review, though, just because I want to make sure this doesn't get lost. If I said graph this, let's say we solve and we get something like this, what does our graph look like? It's just a number line graph. I'll remind you of that. Okay, so we put a 9 on here. Of course, our 0 would be down there someplace. And he said, I think somebody said open circle pointing right. Do you guys agree?
Yes.
Was that you? Okay, sorry.
Wait, yes.
Yeah, open circle because there's not an or equal to, pointing right because it says all values bigger than 9, right? Okay, let's do another one. What if it's a compound inequality, something like this? Go ahead. That's not straight. Now what? Remember that would say x is what?
Me?
Sure.
X is between, including 2 or minus 2, and it is in between 1 not including it.
Good. So how do we graph it? Hudson, how about you?
Like how do I graph it?
Yeah, just on a number line like the one up above there.
The -2 is equal to or less than x. So you put -2 on the line. And then a closed circle pointing right. And x is less than 1. So you put a 1 where that line is. And you put an open circle up here.
Good. Awesome. Good job. You guys remember this? Let's do the interval for this one. Actually, let's do it for both. Okay, interval for x is greater than 9. Remember, parentheses means it can't be the number. Brackets means it can be the number. Remember that? So how would we show x is greater than 9 with intervals? By the way, we're reviewing that because today we're going to start talking about domain and range, and those are interval notations, so that we'll have to be able to do that. Okay, I'll give you this one just to review since it's been a little bit. Remember, we start with the smaller number and go to the bigger number. So this one starts at 9, but it's a parenthesis because it cannot be 9. Open circle says it can't be 9. And then we say comma, we're going from 9 to what? Infinity, good, so infinity. And infinities always have a parenthesis. Infinities do not have brackets. Okay, down here, where is this one starting, the next one? -2. Is that a bracket or a parenthesis? Bracket, since it's filled in, since it says it can be -2. And then comma, where are we going to?
1.
To 1, bracket or parenthesis? Parenthesis. And remember, it was okay if brackets and parentheses were mixed. It's totally fine. Okay, let's do one more. Let's say we have x is less than -3 and x is greater than 4. Okay, let's graph it first. How does this one look? This one's kind of that third case that we saw. Okay, -3, open, pointing left and 4 open pointing right. So we have this gap in between where there aren't values that we include. So in terms of an interval, we have to write 2 chunks. Okay, let's write the interval for the left piece. What is the interval for the left piece? How about you, Luis? Okay, where does it start? This one's tricky. This is the hardest kind. Because remember which way we always read? Left to right. So where, even though the arrow is pointing left, where is it actually starting?
Negative infinity.
Yeah. That one's the trickiest kind. Does negative infinity have a bracket or parenthesis?
Parentheses.
And then 3 also has a parenthesis. Okay? That was the left piece. How about the right piece, Jasmine? Good. And then in between these two, I don't remember if I mentioned this, but we put this little U symbol. It doesn't have a tail. It stands for union, saying, hey, we're joining these 2 chunks, but there's a gap in the middle that we don't include. Okay? So that's, again, domain and range. Those are going to be new words for you today. And those are going to both be written in interval notation. That's how we show them and communicate those. Any questions on that little review of intervals? Does it kind of ring a bell? Do you remember doing that?
Yes.
Okay.
Yes.
So big idea. Anything that it can be, so or equal to or closed circle, it's a bracket. Anything it can't be, so open circle or not equal to, it's parenthesis. Always start from the lower number to the higher number. And that's probably the single most missed issue on intervals. So just reminding you, smaller number, if you want to write this down, and then bigger number. Always go small to big. All right. Well, our new unit, Unit 3, this is a little bit tongue-in-cheek here, but this unit is all about linear functions, okay? And so I highlighted the fun in functions. Do you guys think this is going to be fun?
No.
What? Come on. This is Levi. This is Levi. He's excited about this. No, you don't think so, huh? Okay.
This is gonna be fire.
Fire.
What are you?
Yes. Now, I'll tell you this. We're about to establish a foundational concept that will follow you through the rest of your math career. And that's the word function. Basically, at this level, you're going to kind of think, why don't we just keep writing y equals? But as you grow in this, and as you grow in this year even, you're going to start seeing, hey, functions does make a lot of sense. So we're going to kind of ease into this. Give me an idea of how much you've dealt with this word in math. Have you done it at all?
Yes.
Have you ever called something a function before in math?
I think so. I've called something functional.
Okay, what did you say, Levi?
Nothing. It was outside of Mountain.
What was it?
Party.
Party?
Party at the function.
Pull up to the function.
Oh, I see what you're saying. Yeah. Okay. All right, so Unit 3. Of course, we're going to have to be able to define a function. I'm going to give you that definition in your notes. And then we have these new words, domain and range, that I've told you about. And how do we use functions, all of that kind of stuff. So let's head there and start writing. This is not a really good time to do it. I mean, obviously, if it's urgent, go ahead. But Probably should sign out. Never mind. Just do it. Okay. Linear. Oops, I forgot the S. Linear functions. Okay. Guys, it's hard sometimes in math class when we have a word that we use out in everyday life that doesn't mean the same thing as what we call it in math. And you have to kind of bridge that gap. Like, oh, I know this word out in real life. That's what I'm using it as. And then I got to switch over and kind of think of it differently. This is kind of like that. So like you said, function like a party, right? And that's been around, that definition has been around for a while. We also know that things have functions, like what's the function of a microwave, like that kind of thing, right? So it has a job to do. That's kind of like this. We're going to start by defining some build-up words to it. Well, just one, really. And that first word is, or that first concept is a relation. So this is just a set of ordered pairs. Ordered pairs are just x and y coordinates, which we've been doing a lot with, right? Can you not see? Okay. Is that any better? Like just barely? That's okay? If I stand kind of right here like this? Is it okay? Okay. A set of ordered pairs, which are just xy coordinates, so think points, right? Excuse me, that's all they are. So, like some examples.
I think the best example would be like a box with X's on the top and Y's on the bottom.
Okay, do that.
Okay.
I am gonna give you like a point. Remember, it's always xy. If we start combining a bunch of those, so let's say now we're gonna do 5, 6, or not or, but and 9, 10 maybe. Okay, if we start combining a bunch, that starts to become a relation. Like we're saying, hey, look, each of these x's has a y partner with it. Okay, for us to call it a relation, or to see it as one, we're going to put these around it. Do you guys know what those are?
They're like, I think they're like brackets, but like twisted.
Okay, I'm going to redraw this first one. I didn't do good. Okay. Here, I'll draw it really slow. Ready? And it's hard because you can't see my hand move. Basically, start like you're going to do parentheses. I can't hold it. Make a little V and then do another one. That's all it is. So it's like a parenthesis stacked on top of a parenthesis with a V in the middle. A sideways V, right? So parenthesis, V, parenthesis. And then on the other side, same thing. Now, these have names. They're called braces. Yeah, technically. Yep.
Brace as in like the stuff in your teeth that the doctor puts in it. Those are braces, but this is also a brace.
So when we say use braces, that's what we're talking about. And that stands in like contrast to brackets and parentheses, right? Now we have three things to group numbers together. All right. So you've dealt with relations forever, right? Like if I said, hey, you have a height of your body and a arm span, like that could be a relation. Everybody in here, we relate our arm span to our height, right? So like a width and a height of ourselves, kind of. Or maybe a relation saying, it doesn't always have to be numbers, by the way, but a relation of I work 3 hours or 3 days and then I get 4 days off or whatever. I don't know. There's a million ways to think of this. So it's just a set of ordered pairs. Okay? Let's get into what a function is because it builds on that. And in a very specific way. I'm going to put a box around this because this is a pretty important definition for us. Like I said, for the rest of this year, but also going forward, especially in Algebra 2, those of you, well, most of you will end up taking that. So a function now becomes a relation where, am I still in your way? You sure? Yes, I am in your way? Yeah, well, I just keep seeing you lean, so. All right, a relation where each inputs are x values. And I want you to underline the word input because that's kind of its own vocabulary word. It's just an easy one. So each input gives, and this is important, so I'm capitalizing it, exactly one output. And outputs are y values. So in this, we take a relation. Remember we said a relation is just a bunch of ordered pairs. Inputs and outputs, we could also say. A function now narrows that down to say, well, each input can only give one output. So let's think of it, a couple examples. We'll put some in, but we've been dealing with lines. All of our graphs have been lines. Is a line a function? If I give you an x value, does it create just one y value or does it create more than one y value? Just one, right? And don't draw this because we'll put it somewhere else. But if you just think of putting a line on a graph, if I pick this x, it gives me one y. If I pick this x, it gives me one y, etc. It never gives me more than that. Okay? So if a line is a function, what is not? Have you even ever seen one that's not a function?
A vertical line.
Okay. So a vertical line. If I pick an x, I get a whole bunch of outputs, right? Like infinite. Good job. What else? And don't limit yourself to just like Algebra 1 graphs. Just think of things you could put on a graph. Yeah.
What about like a line that doesn't go on infinitely, like a triangle or a square in the plane?
Okay, yeah. Like if we could to graph a triangle, which you can do, you'd have to do what's called a piecewise function, and you'd have to graph it in 3 pieces. But then it wouldn't be a function, right? Let's do one like this. This is an easy algebraic equation, and that's a circle. Is a circle a function?
No.
Why not?
Because one x input gives 2 y outputs.
Okay, let's say I pick this x right here, whatever it happens to be, maybe it's x equals 2. Do you see how it would go up and give me an output up there, but also it would give me an output down here. So we end up with a y value up there and a y value down there. It gives 2 outputs. So it's not a function. Does that make sense? Okay. Similarly, if we happen to have some curly function like this, curly graph, I should say, would that give a function? Would that be a function? No. Again, it wouldn't, because like if I pick this x right here, I'm getting 1, 2, 3, 4 y values. Definitely not a function.
I
Okay?
think I know what the definition of a function is. Like in a visual sense.
Okay.
If you have a function, the lines never overlap each other.
Vertically.
Yeah, vertically. They can overlap each other probably. Would it be possible to overlap it?
Yeah, here's what he's
on
saying.
On an X line?
If we have one like this, is that a function?
Yes.
So he's talking about the overlap, meaning like we have repeated values going left and right,
Oh,
right?
Yeah,
Is that okay?
yeah that's all right.
That's okay because each x, like if I pick this x right here, it gives me one output up there. And same like this x gives me the same output, but it's a different x, right? So yes, that's a function. So I think that's a good way to think of it. What was it? What did you say again?
I said that
If it overlaps?
yeah, if it
Okay.
overlaps on the y-axis, if you like squish it down and the lines start to converge, then it's no good.
Yeah, that's good. Let's think of it that way. Good idea. So part of this, guys, will be, hey, is it a function? I'll give you a graph and you can just say yes or no. And then part of this is also asking, like, well, I don't want to get into that. Basically, we take this and say, write a function, use this function. And so what I want you to kind of think of this as is a new word for an equation in some sense, okay? It's kind of saying we're relating an x and a y in some way. So in your notes, I'm going to tell you to start thinking that way. Now I'm back in your way again. So start thinking of the word function as a relationship between, I can't write that, between, there we go, x and y. Where the function takes x, which is an input, does something to it, and gives y, the output. So by that description, do you see that you've actually been working with functions for years now?
Yeah.
Interesting, right? So let's do a quick example.
If you press the attack button on a keyboard, the video game will show you attacking and putting the monster. Yeah.
Yeah, and honestly, like in that kind of world, that would be a function of an input, right? So he was saying the input is your input on the controller, and the output is the thing doing the response to your input. Or whatever you said, attacking the monster. Okay? All right, let's do a super familiar kind of version of this. What kind of situation is that equation I just wrote? Just tell me everything you know about it.
It's in the slope.
There is
So we know a slope. The slope is 5, just 5. Okay, what else do we know?
the y-intercept is 10,
It has a y-intercept of 10. Okay.
and that
If I went and said, hey, everybody, graph this, what would it look like?
It would be a straight, it would be a function,
Okay. That looks like what on the actual graph?
just a straight.
What would I come around and see on your graph paper if I saw this? It's a
Linear
Line. Yeah, linear. It's a line, right? It's just a line. You guys are telling me like up 5/1. Good job. That's the slope. It starts at 10, etc. Okay. Shift your thinking a little to input and output. What does this do to the input? Just describe it in casual language. So this function does what? I'm going to tell you that x is 2. What is this function going to do to the 2? Don't overthink it. I promise it's not, I'm not asking you a trick question. If I tell you 2, x is 2, sorry, go ahead. Okay, we're going to say, stop there. This function multiplies the input, which is x, by 5. Okay, that's what Abby said. So times by 5, and then what? And then what?
And then add 10.
And then add 10. Okay?
Did you say adds or just add?
And then adds. You're right, we're talking about the function. This function multiplies the input, which is x, by 5, and then adds 10 to give y, which is the output. So, if I tell you x is 2, what is this function spitting out as the output? What is actually the output value? Everybody.
Yeah.
I know, but what's the value, I mean? So if I say, oh, x, I'm putting x into the function, x is 2, it comes out, and it's what? It's 20, right? So it's 20. So that's the idea of a function. It's taking input, doing something to it, and spitting it back out as output. And that's what we've been doing for all of our work, actually. It just hasn't been called that. So let's pause there and go look at some of these. I'm going to erase, actually I can't erase that. Just ignore that statement real quick because I haven't told you what 1-to-1 means. We'll come back and do that. Oh wait, that's domain and range. Okay, before I tell you about domain and range, I don't know if we'll get to that. Does this look to be a function? What's in this table?
Yes.
And what is telling you that it is, besides the fact that it says the function? If I plug in 1, do you see how I get 1 output? Same with these other ones. Okay?
Wait a minute.
Okay.
Is that a function? I don't think that's a function because multiple x values are giving the same.
Okay. However, our definition said each input gives 1 output.
Oh.
Is that true even though these are all 13?
Yes.
Yeah, 3 is just giving 13, 4 is only giving. So how would this change if we said, okay, let's make it not a function? And you guys just tell me, I'll add it up here. Let's say I'm going to continue this table. Give me a way that I could put some numbers in here that would change it to not be a function.
Adds.
5, 14.
Okay, here's what Abby said. 5, 14. Why is that now failing to be a function? Yeah, well, kind of. I added to it, right? Go ahead, Jesus. Yeah, do you see how 5 now is spitting out 13 and 14? Okay, everybody see that? Okay. So just to introduce you to this, you don't see it a lot after defining functions, but in your notes, go to the first example box. And we have little maps, I don't know if it's called a map, that help us to think through this. So I'm gonna write and then I'll move. Function or not. You kind of start off with these little input-output maps. Blech. It's supposed to be an oval. Wonder if I could actually draw an oval.
You're drawing an egg.
There we go.
Yellow.
Just do your best. That was such a bad oval, it didn't even know it was an oval. It thought it was a rectangle. And by the way, I'm just making up numbers. There's no magic to this. It's just, we need some numbers. Okay, so you could even just make up your own. Just, I want you to put 2 different ovals with different numbers. Okay, we said y was the output and x is the input. So, here's the concept behind a function. Actually, I'm going to show you what I'm going to do. I'm going to start drawing arrows from input to output. And what do we have to be careful to not do? Yeah, exactly. Okay, so go ahead and just draw arrows across. And if you want, you can have 2 inputs go to the same output, like I did. So 6 went to both 5 and 6 went to 14. Let me make that a little bit more obvious. So this is a function. Now we're going to make a box that's not, or make a section of this that's not. I'm going to give you time. I don't know if I can actually do that. Never mind. So let's just do it together. Do the same box over here. Same ovals. Okay, I want you to draw arrows in a way that makes this one not a function. And there's lots of ways. So I'll let you do yours, and then I'll put one that may not be the same, but it will at least verify. Okay. So here's the big idea. Already that's not a function. Why? Yeah. That 3 is pointing to 2 different things. So 12 and 13, right? So even if the rest of this is okay, I'm not going to make it okay, but even if it was, it's not a function. We have multiple outputs for 1 or 2 of our inputs. So again, this is kind of a concept map. Obviously, these aren't graphs of actual functions, but it's conceptually, it's saying, hey, if I put this input in, I can't have 2 outputs for it. Here's how some people describe this. If you look up here, if you're defending this blue castle, let's say, each archer can only shoot 1 arrow. If they start shooting multiple arrows, it's no longer a function. Okay. Okay, let's do more of a graphical example. Kind of like we did a second ago. Now, I'm not going to do all of them. Like, this is just going to be a couple example graphs.
I have a question.
Okay.
What if an input doesn't give an output?
Okay.
And
And so what are you saying? What if what? What if what?
what if, like, x didn't have a y value?
Well, I know, but I guess what I'm asking is, what is your what if asking about? Like, is it still a function? Is that what you mean? Because it's okay if some of our inputs don't give an output. In fact, here, look, I'll just draw this for a second. We might have something like this curve, and then we have an open circle where there's a gap. This is still a function. It just has a point where it's not defined. In fact, in Algebra 2, you learn about some that are kind of wonky looking, like that. And so it's a function on its domain, but there's this, what we call an asymptote, where it doesn't exist, but it exists everywhere else. So it's still a function.
Oh, like, it's kind of like a minus infinity number union
Yeah.
number minus infinity.
Like we could graph this one as 1 over x. So do you see how everything is okay except 0, because we can't divide by 0. And so at 0 it falls apart, but everywhere else it's okay. So it can still be a function even with those holes, or we call them actually holes or asymptotes. Yeah, good question. Okay. Let's draw the sine curve. Okay.
Basically a circle.
This keeps going forever and ever.
Shifted.
And it is y equals sine of x. If you have a graphing calculator and you push the sine button and you went and graphed this, that's what it would look like. And again, it just keeps cycling forever and ever. Is it a function?
Yes.
Yeah. Each x gives 1 y. That x gives 1 y.
Is
That
sine
x
like a number?
gives 1 y, etc. Okay, so yes, it's a function. Sine is a function. It's not a number.
Because when I type sine in by itself in the calculator, it gives out a weird number.
Yeah, because... How about I tell you about that later?
Oh, okay.
Okay, let's do one that's not. Get in the habit of labeling those axes, x and y axes. Okay. Something like that. This is not a function. Why? Yeah. Okay.
What equation would make that?
This is called, well, there we go. These kind are called trig functions. So sine, cosine, tangent. If you've seen them on your calculator, it's sin, cos, tan. Those are actually shortened versions of sine, cosine, and tangent. And then if we take the reciprocal of those, we get secant, cosecant, and cotangent. That's what makes those kind of graphs.
Oh.
Don't worry about what it is. I mean, it's cool that you're asking, actually. Okay. 1x. 1x gives more than 1 y. So not a function. Most of the things you guys have done in math to date in your life has been a function, right? A lot of it has been lines. This year we're going to study linear functions, we're going to study exponential functions, and we're going to study quadratic. And just to give you a heads up on those while people are finishing up, the exponential function looks like this. And the quadratic function looks like this. It's called a parabola. So just to look at those, are those both, I keep saying it, but are they actually functions?
Yes.
Yeah. If I pick one x, it comes and hits the graph just one place. Yes, Jackson?
Does exponential always have to start in the negatives?
Yes. Well, yes, it will always go that way unless we do exponential decay, which then it goes down instead of up.
A few questions.
Okay.
First of all, what would rooting look like? Like dividing number by root or something. And the equation for a quadratic function.
Yeah, the equation, this one is just y equals x squared. That's the basic version.
Mm.
And then a square root function looks like this.
I thought it would be like.
That's square root of x.
I thought it would be like.
Now, if you say, what's the cube root? If we put a little cube, now it curls down and goes that way. So all sorts of stuff, right?
Is there an opposite to the exponential function, like where it
Yep.
starts up by infinity and then goes down?
So exponential is e to the x. Well, e or 2 to the x. Let's just do 2. It goes like that. And then the inverse or the opposite of that is, we're getting into some weird stuff, but is that.
Mm.
Okay? So the green one is the opposite of the blue one, and it does that.
What's log?
See? Wait, we can talk about it like individually, but that's all stuff you'll learn in Algebra 2. It's cool stuff. Trust me, it's cool. All right. In our last few minutes, let's take a moment just to write down what domain and range are in your notes, please. And guys, this is a big idea as well for this class, but also for your next math class. Domain is the set of all input, which we know is x, values used by the function. So domain, underneath that word, I want you to write x. Just because that way on like a quick glance, you'll remember, oh yeah, that's x.
And range, I'm assuming, is the opposite. It's y.
Indeed. Range,
The
the set
of
of all what?
y.
Output, which is y values. Now we can't say used by the function, we have to say produced or created, yeah.
It's pretty neat.
Yep, so underneath range, put a y. Okay, we'll talk more about these. Obviously, we'll get into name or like writing them out and stuff. But just know that these are intervals. Interval notation for both. Good job today, you guys. You were very engaged, asked good questions, so thank you.